I'm Saraswathy, an MTech research student from Indian Institute of Science. Today I would like to give a brief overview of our work Latency Redundancy Trade-off in Distributed Storage Systems. This is a joint work with Professor Parimal Parath and Vikram Srinivasan, an adjunct faculty at ISC. This work is funded by Cisco Center for Network Intelligence. A distributed storage system is a collection of standalone servers that have data distributed over them. In such systems, data is stored redundantly in more than one server for improved scalability and tolerance to failure. Distributed storage systems have a wide range of applications ranging from video streaming to military applications. Some examples of distributed storage systems are Oracle, MongoDB, MySQL, etc. We observe that master-slave is a common architecture adopted in these systems, where the data is first written to the master before being copied to the slave servers. Since all servers now hold a copy of the data, it can be read from any of these servers. Hence, an increase in redundant servers will lead to a decrease in read latency while increasing the write latency, since the data now has to be copied to more number of servers. This leads to a trade-off between latency and redundancy. It must be noted that the latency performance of a system is an important parameter that could lead to loss of revenue if not designed properly. In that regard, we study a distributed storage system with master-slave architecture with Poisson arrival of read and write requests. We assume that read and write requests are served exponentially at each server. Further, we consider a system where one class of request has priority over the other and the higher priority request preempts the lower priority request on arrival. Our objective is to characterize the trade-off between latency and redundancy in order to obtain optimal choice of redundancy for the system. As can be seen from the figure, an incoming read request is routed uniformly at random to one of the servers in the system. The incoming write request, on the other hand, first joins the queue at the master server. Once the write is completed at the master, the request gets forked to the slave servers at the same time. The write request leaves the system on receiving service from all the servers. This is essentially a fork join queue. A fork join queue can be equivalently written as a series of tandem queues, and the write latency becomes sum of latency from each of the tandem queues. We obtain closed form expression for read and write latency in the system by approximating the system as a series of uncoupled tandem queues with independent service rates. From this expression, we identify the optimal number of redundant servers that minimize latency under different load and priority conditions. The main contributions of our work are the following. We characterize the latency-redundancy trade-off in distributed storage systems by accounting for latency from both read and write requests. From the closed form approximation obtained, we provide guidelines for system design by studying the variation in optimal redundancy for read and write priority systems under varying load. We study read and write latency separately while accounting for the influence from the other request class. Hence, the user can choose the right optimality for their system by weighing the read and write requests differently depending upon their application. With that, I'd like to conclude my presentation. Thank you.